Welcome. The title of today's notes worksheet is Transformations of Functions Day 1. And you will be responsible for 10 transformations when all is said and done here. I believe 6 are going to be presented on this notes worksheet, and then another 4 presented on the Day 2 notes worksheet. So what we're going to do is just start out with a little investigation to get us thinking about it, and then try to fill in a table so it can be a good reference for you as you go through learning all of these transformations. So let's start it out. It says, use the following parent functions to investigate 10 transformations of functions. That sounds great. Any function can be a parent function. I just figured we would go ahead and just use some of the basics from each family to get us going with this. And remember, you should be fairly comfortable at this stage understanding all the graphical patterns of each of these families. So, obviously the quadratics form the parabolas there. And, the most basic one is just y equals x squared. So let's go ahead and just kind of fill these in piece by piece. Cubic family right here, just doing y equals x cubed, something like that. We'll see some absolute value stuff. We don't do a ton of application with absolute value, but it works really well with the transformation, so you'll see this over the next couple days. Same with the square root family. The square root family, not too many applications that we do, but it works really well with transformations, so you'll see them over the next couple days. So again, just comfortable with the graphical patterns that emerge. Okay, here's a nice exponential curve right here, something like this. Seen it a couple times before, and maybe see a linear every now and again too. So just the most basic one. Let's see if I can get that through. There we go. Y equals x. Probably won't use the hyperbola very often just because the graphs can get so convoluted, especially when you start putting more than one on a coordinate plane. But certainly would be viable. Cube root 1 is actually a good one as well. Okay, so let's see, have that. And that would be the cube root function, by the way. I don't think we talked about that on a previous notes worksheet. But this also does work well with transformations. You will see in the future a nice connection between cube root function and the cubic function. But for right now, again, we'll just kind of deal with it in terms of being a parent function and potentially transforming it. All right, so we'll just kind of use those. You do need a graphing calculator, certainly, for this lesson. And what we're going to try to do is get all 6 in this nice table that I provided for you. That way it's in one spot, all the information, and we can utilize it appropriately. So I have 4 columns in this table. The first one would be the names of the 6 transformations. We'll kind of fill those in. You're going to have to get very, very comfortable with the notation here. And when you see a particular type of notation, understanding which transformation that represents. And we're going to do it really from 2 different perspectives on a function. We're going to talk about it as changing the equation and then changing the graph. Now, I sort of think about it in these terms. I don't know if this is ideal by any means, but I sort of thinking of it as a cause and effect. These are really 2 separate ideas. I'm going to initiate a change on the equation of the function. And what's that going to produce is some type of graphical effect or graphical consequence. And that's what I want to get comfortable with. When this happens, when I initiate this, what happens over here? And so that's what we'll take a look at. All right. Now, the way I've done this in the past is basically by giving the notation column. So all the way through, I'm going to give you these 6. And then for us to hopefully try to fill out these pieces together. There's a lot of great word association that goes with this, and we'll kind of talk about that through the process. But think about input versus output, and think about what that's going to mean graphically. Think about what that's going to mean in terms of the equation, all that stuff. This is where I hope some of the preliminary work pays off. Okay, well, here we go. So let's go with our first notation. So if you would, right next to this, this is basically going to be our new function. And what we're going to do is take our old function, that's going to be f of x. So y equals f of x is what's called your parent function. It's a way to just kind of define what you're starting with. So f of x is our parent function. But now, everybody, what I'm going to do is create my new function, just this generic y right here, by taking the old function and adding a constant. So plus c on the back. Now here, of course, is the great question, and going through the word association I think pays off here. does this look like I changed x or did I change f of x? And if you're not sure, you'll be able to kind of compare and contrast as we work our way down. But what I would argue is it looks like we're not changing x. X is still the same, right? But we are changing f of x. I'm adding a number to f of x. So if I'm adding to f of x, it is an output change. So if you would, can you just put output right here? And what does that mean specifically? Well, as you can see, the notation I think speaks for itself. Let me just make sure I have this right. I am adding c to the function. Okay, so whatever f of x is, the function itself, I'm just going to add a number on the back. And so we're going to go ahead and kind of start this out right here. And let's go ahead and get the graphing calculators. What is the graphical consequence? What is that? What would you call it? What's the name and all that stuff? So go to your y equals, and if you have anything in there, clear that out. And you know, I'm actually thinking the cube root function works great for this one. So let's do that. So if you would, go under the math menu for me. And you see it's that fourth one down. There's the cube root. So I'm going to hit number 4 and just do cube root of x. And I'm just going to quickly zoom standard this. And, you know, that's what I drew at the top. Okay, now everybody, here's what I'm going to do. I'm going to take that exact same function. And that's what it says up here. Let me go back to this for a second. It says take your function. The original function was cube root of x, everybody. And I'm going to take that original function and I'm going to add a number on the back end. I'm going to keep things nice and simple here. I'm going to add 4 on the back end. So instead of cube root of x, it's cube root of x and now a plus 4. And that's all it is. I'm adding a number to the original function. Well, I'm going to hit graph here and take a look. So this was the original. This is what's called the parent function. This is the transformation function right up here. And what would you call it? What do you think? What happened to all of the points on this one? In fact, the infinite number of points on the graph of this initial function all changed in the exact same way. Well, I hope you see that they basically moved up. Every point moved up 4 units. In fact, that's what we're going to write in here. I hope you all agree that if it moved up, that is a change that is vertical in nature. And sometimes this is called a vertical translation, but we are going to call it a vertical shift. And I'm going to put up right below there. So that is a vertical shift up. Everything moved vertically 4 units up. Okay, now again, notation, word association, let's put it all together right here, including the graphical change. I think I gave this away basically by saying every point moves up that many units. If I put a plus 5, it would have moved up 5 units. If I put a plus 10, it would have moved up 10 units. So every point moves up that many units, whatever C is. Okay, now let's put a couple things together with this because it really falls into line nicely. And if you can get this word association down, you have a better shot at sort of memorizing or learning this particular table. So first and foremost, output, guys. Output is something that is vertical in nature. So output affects the y's. And so as you can see, output is going to be a vertical transformation. Keep that in mind. As soon as you know it's an output, you know it is some type of vertical transformation. And what that means, of course, is the points are going to move vertically. And so which I should say ordered pair changes. So let me just bring up the graphing calculator one time as you're thinking about that. So this point moved from here to here. In terms of the ordered pair from here to here, which coordinate changes, everybody? It was here, now it's here. Well, it looks like x is the same, but it looks like y is different. So the y values moved up, basically, 4 units. All right, good. So, again, output, think vertical, think y. All the y values changed. All right, good. Let's go get number 2. Here's the good news. Similar notation. Instead of a plus, let's go ahead and throw a minus on it. Now again, does that look like an input change or an output change to you? I would argue output. X hasn't changed, it's still X. It's f of x that's changing by now subtracting c. So everyone, if you would, output. So right away, let me be very clear on that, you know this is going to be something vertical. So in this case, it looks like we are subtracting c from the function. And you could probably guess what we're going to call this one, but if not, no worries, let's get it going. So let's do the same one, just might as well make this efficient here. So let's start out with cube root of x, and in this case, instead of cube root of x, let's do cube root of x, I'll just do minus 2. How about something like that? So subtracting a value from the original function, I hit graph, there's the original, and as you can see, here's now the transformation function. And as you can hopefully see, everything moved down to, it vertically shifted, just down. So there's your number 2. Again, not too bad, right? One's moving up, one's moving down. The plus is up, minus is down. Cool. And again, just output, it's the y's that changed. So if I asked you about ordered pairs, which I will on the back side of this sheet, definitely, every point moves, there we go, down c units. So we'll talk about those ordered pairs when we hit the back side. All right, looks good. 2 down, 4 to take care of. These, for the most part, will work in pairs. Let's go ahead and get you notation number 3. And I think I will do this one first. Okay, notice the subtle difference in the way that's outlined. So y equals f of x plus c. What does everyone think here? Input or output? And I guess I would say the x has changed. It's no longer x, it's x plus c. And so as a result, it seems to be an input change. And remember, input and output changes are different in how we work with that mathematically. So here's what I would say. Remember how we have dealt with input changes before. We replace all of the x's with x plus c. That's what it basically is saying. So x plus c would be the input to our function. It replaces all of the x's. Now again, just putting it out there, as soon as you see input change, think of all the words that go with that. Input, everybody, means it's going to be something that is horizontal in nature. The x's are changing in a particular way. So I can probably safely say here this is going to be some type of horizontal transformation. Not sure what that's going to be, but let's figure it out. All right, let's bring the calculator up. Let's change functions there. So go to that y equals if you would. And trying to think, what would be a good one right here? You know what, the absolute value one would be great. So let's do this. If you could go to math, move it over 1 to the right, and go ABS, absolute value. So I'm going to do absolute value of x. Now again, what I'm going to do is replace that input. So let me go back and get absolute value going. Instead of absolute value of x, let's do absolute value of, say, x plus 3. Everyone okay with that? So I changed the input from x to x plus 3. And the question, of course, becomes, what happens? There's the original. So let me see. Here's our v. There's our original one right here. And here is the transformation. And it looks like those points, all of those points, by the way, are moving to the left. And so as a result, I'm hoping you see that this is what we would call a horizontal shift. Every point moved the exact same number of units. In this case, it moved it to the left by 3 units. If I did a plus 4, it would go 4 units to the left. 5 units to the left, etc. And so as a result, let's go ahead and put this in. Every point moves left. That's the key, c units. So I'll kind of give you a heads up as to how this works. Again, input changes are quite a bit different than output changes, but just be careful on this. Plus is a transformation to the left. Keep that in mind if you would. I've seen students over the years confuse numbers 3 and 4 here. Okay, we're filling in our table pretty nicely. 3 different notations. It's time to go ahead and do 4 and 5 and 6. I think you could probably guess what 4 is going to be. Let's go ahead and do this right here. There you go. There is number 4. Input or output, everybody? Oh, it's got to be an input change. It's no longer x inside the parentheses. It's x minus c. So the input has changed. So I guess remember how to deal with inputs. I'm going to take all of the x's in the function, and I'm going to replace them with x minus c. Okay, looking good. Let's keep filling in. Now I'll bring my graphing calculator up. Go back to that. And let's keep the original there. And what do you say? Instead of x, why don't we do, say, x minus 5. Something like that should work. And I hit graph. And take a look. Here's the original. Good. Here's the new one. And you can hopefully see every single point has moved to the right 5 units. So this would be a shift, horizontally, of course. Anything input is horizontal. Anything output is vertical. Anything input affects the x values. Anything output affects the y values. Keep that in mind. That is huge for this topic of discussion. All right, so we have our 4 directions, basically. We've run out of directions here, so you know 5 and 6 are going to be different. But let's go ahead and get this in. So every point moves to the right. So just, again, be careful on this piece, please. Plus moves it to the left, and minus moves it to the right. Potentially on the next notes worksheet, I'll kind of go into sort of why that is in a little more detail. But we saw that graphically. I mean, it really spoke for itself. When I did a minus in replacing that input, it shifted that graph to the right. Okay, 4 directions down. Let's go ahead and get a different type of transformation going here. So, number 5 notation. Here it is, everybody. Be ready for it. Okay. So we have seen this before, just working with it mathematically. Now, we can actually put it in terms of an application. So f of negative x. And what would be your guess here? Input change or output change? Well, I would definitely say this is an input change because I no longer have x in here. I have a negative x in there. So it is an input change, which means, of course, just in terms of working with it, replace all the x's with basically a negative 1x. That's the way I like to describe it. So replace all the x's with negative 1x. And when we do that, what happens? Well, let's see. Let's see if we can name this one. Let's go back. Let's change families here. I'm going to do the exponential one. Looks good. So 2 raised to the x. Now, because I want to go ahead and transform this according to this notation here, all I want to do is change the input from an x to a negative 1x. And so that's all you have to do right there. And so what happens when we do that piece? I'm going to go ahead and hit graph. There's the original. There it is. And here is the transformation. So as you can, of course, see, it's not a shift, but by no means. It hasn't moved in the same direction, the same number of units. What is it? And I can kind of show you a few points here. This point moved here. This point moved here. This point actually moved here. So this point moved here. What do you think we would call it? Definitely not a shift. Okay, it is actually a reflection. This is reflected over to here. And what is reflected? What is it reflected over? Well, it looks like it's the y-axis right there. So if I flip this over the y-axis or reflect it over the y-axis, I get my new point. And that is number 5. It is a y-axis reflection. So it is an input change. Let's be clear on that piece. And it is the x's that have changed. So let's bring that graph on up and let's be specific. What was the true graphical consequence here? What happened to all of the original points? So as we said, they reflect over the y-axis, but what changes when it reflects over the y-axis? Think about that for a second. When this point moved here, did the x-coordinate change or the y-coordinate change? Well, this one right up here, whatever this is, it looks like it's just the opposite x value, same y value. So again, this point right here, change the x, and now it's over here. And that is exactly what our description is going to be. So here's what I wrote on my paper. Every x-coordinate changes to its opposite. And that's exactly how this falls in line, guys. If you look at the notation, that is an input change. And look, the notation kind of speaks for itself, right? Didn't x change to negative x or the opposite of x? And that's by description right here. All the x's change to its opposite. Good. Input, x is going to change. If it's an output change, the y values are going to change. All right, good. We're ready for number 6, last piece. Hopefully, maybe you can use a little intuition on what this is going to look like. There is number 6. There is the notation. So a negative f of x. Okay, very good. What do you think? Input or output here, everybody? Well, x is not changed at all. It looks like f of x is changing to its opposite. So it is an output change. Let's get that in there. And again, output changes are different. So here's what I have. Basically, if you can kind of look at it, we're going to multiply the function by -1. So we're basically just putting a big opposite symbol out in front of the function, and then we're going to distribute it in. It's the same as basically saying we're going to multiply it by -1. All right, so output change on that. That's looking ideal. Let's go ahead and put this into the mix. See it graphically, name it, talk about the official graphical effect, and go from there. Let's do the same one. Just works well. So instead of 2 to the x, basically all I'm going to do is, as the notation says, take the original function and just put a negative symbol out in front. Now here it really just, oops, wrong symbol. How about a negative there? And 2 raised to the x. So I should put this in parentheses really just to emphasize that piece, although it really doesn't matter in this case. But I'm going to go ahead and do that. There's the original, and there is the transformation. Looks like another reflection, doesn't it? And in this case, it is an x-axis reflection. So an output change reflects over the x-axis, because when something reflects over the x-axis, it's the y-coordinates that change to the opposite. And look, here it is. Remember, f of x really just represents the original y-coordinates. And now I'm just going to change them to their opposite. So let's just go ahead and take a quick peek here, maybe at a point or two. I know a few values there on the original. This would be 1, 2. And now, as you can see, it's 1, -2. This one, everybody, is 2, 4. Now it looks like it's 2, -4 down here. All the y's change to the opposite. Again, as soon as you see it's an output change, you know the y values are changing in some way. And the notation typically will allow you to kind of figure that out. So every y-coordinate changes to its opposite. And there, everybody, there are your 6. Looks great. 4 shifts, 2 reflections. The other 4 come on the Day 2 notes worksheet. Let's just get a little practice with them. So to me, there are really 2 types of problems that go with this lesson, and tomorrow's, of course. It's working with the equations, transforming them that way, initiating the change, and also working with it graphically and seeing that graphical change there. So equations and graphs. Those are the two types of problems you'll see, and they'll pretty much match up with the examples that you see on the back side. So at this stage, just from an equation standpoint, I should be able to give you any function, and any function, by the way, can be a parent function. I should be able to give you any of the transformations we've seen, and you can give me the new function that would make it happen. So let's try it. So here's our parent function right here. Here's what I want to do with it. I want to take the graph of that parent function and move it to the right 5 units. Can we do it? Yeah, let's see. Now, keep using the table, guys, back and forth with this. The first thing to kind of figure out, when you want to move it to the right 5 units, is it an input change or is it an output change? And word association, it really helps here, everybody. Moving to the right is something that's horizontal. Anything that's horizontal is an input change. So here's what I would do until you get really good with it. As soon as you figure it's an input change, circle the inputs. In this case, there's just the x. So circle it. You are going to change the input. You're going to change x. And the question, of course, becomes, how do you change x if you want to move it to the right 5 units? So I'm going to create my new function. The 2 obviously is going to stay. It's only x that changes. Look at the table on the front side. We wrote it all in that table. And it says, if you look carefully, replace the x's with x minus c. And this, of course, is our c. So instead of x, I replace the x with x minus 5. That's the key. That should initiate the transformation. So 2, instead of times x, it's 2 times x minus 5. Everything else is the same except the input change. And let's go ahead and figure this out here. So I hope everyone's okay with me distributing 2x minus 10. And if I do a 2x minus 10, how about the minus 1 there? If I jump the gun a little bit, my apologies, but I'm seeing the absolute value of 2x minus 11. Just cleaning up inside the absolute value symbols. Well, you know, the nice thing about these problems from a student perspective is you'll know if you got it right. It's an easy way to figure it out. Just graph it. So let's see. I'm going to do this. You don't have to. I can do this rather fast. Absolute value, 2x minus 1. I go right on down, everybody, and I do absolute value, 2x minus 11. And if we did it right, here's the original, here's the new one, and you see it move to the right 5. Did it. Perfect. All righty. Letter B. Onward. So new transformation, huh? New function. Let's see. First order of business. As soon as you see this and you need to initiate this transformation, ask yourself input versus output. And in this case, anything that's moving up is a vertical transformation. Anything that is a vertical transformation is an output transformation, an output change. And so what it means to change the output, as we have seen before, is you change the entire function. So do me a favor, circle the entire function. And so what we're going to do is not change x, but change the entire function. And in this case, if I want to move it up, what was it, 2 units? If I want to move it up 2, there's my original function. As you saw from the table, all I do is I add a number to the entire function. And that's it. I clean it up as need be. This one is relatively straightforward, I think, because all we have to do is that. By the way, I'm going to box these up just to make sure we're clear on our answers. And that's it. Nice and easy. Are you affecting the input or are you affecting the output? If you make that determination, you're halfway there. Okay, letter C. This one's a tricky one just because of this little letter right here, but look at the table and you ask yourself, is it an input change or an output change? And a y-axis reflection would kind of affect it horizontally. I almost said it, sorry about that. If it flips over the y-axis, Those points are moving horizontally. And so as a result, it is an input change. Input, input, input. So let's circle the inputs. Again, until you get really good with that piece, I would continue to do this. And then let's ask ourselves, well, how do I affect the inputs if I want to reflect it over the y-axis? And if you look at the table, again, it is summarized right there. It basically says take all of the x's and replace them with negative 1x. So I do a negative 1x cubed like that, and then a 4 times the negative 1x. That is it right there. Now, I am going to kind of keep you accountable for simplifying things, removing parentheses, all that good stuff. I've been doing it so far and will continue. So let's go ahead and work with this and then work with this. I like this piece. And remember, think of this as a negative 1x. And this is an exponential property we've seen before where I would do negative 1 cubed and I would do x cubed in order to remove the parentheses. Well, when I do negative 1 cubed, it's still negative 1. So guys, put a little negative out there. And when I do x cubed, obviously, that's x cubed. So by removing the parentheses, as a matter of fact, algebraically, this is the same as this right here. Good, so I have a negative 1 times x cubed, and then plus 4 times negative 1x. I hope everyone's quick with that one. How about just a minus 4x? And that looks good. If I want to create a y-axis reflection on that function, there it is. Looking nice. Okay. Input versus output. A couple more coming our way. So nice linear function, not too bad. Again, all different families we can work with. So here we go. I want to perform an x-axis reflection on this. And is it an input change or an output change if I want to do that? Visualize it, guys, visualize. If it's going to reflect over the x-axis, kind of from here to here, those points are moving vertically, aren't they? You know, either moving up or moving down. It just depends. So they're moving vertically. Vertical is output. And so as a result, circle the function. I'm changing the entire function. And so the question, of course, becomes, how do I change the whole function here? If you look at the table on the front side, it basically says take a negative and put it outside the function, really multiplying it by negative 1. So this was the negative f of x, the opposite of the entire function. And let's go ahead and take a look. So opposite of negative 2x is 2x. Opposite of positive 4 is minus 4. That looks great. That one's a quick one that we can check. So I'm going to bring up the graphing calculator there. And let's see, what was our original there? Got that, got that. So we had a negative 2x, and how about a plus 4? And then I believe we came up with 2x and a minus 4. And let's see, is one an x-axis reflection of the other? Oh, absolutely. Look at that. So it looks like this was our original. Take all of those points and reflect them over the x-axis. And notice they move vertically. Output change. Oh, it all is coming together. All right, last one of this example. So, quadratic, and I want to move it left 3 units. I am not a nice person. Watch what happens here. Goodness. All right, but let's get the basics down. I want to move it left 3. Left is something that's horizontal. Something that's horizontal is affecting the x's. It's affecting the inputs. So without question, input change. Circle the inputs. Okay, now the question, of course, becomes, how do I affect the inputs? I am going to replace those inputs with something. And the question is, what am I going to replace them with? So instead of x, if you look at the front side, I replace them with x plus c. So instead of 2 times x squared, it's 2 times x plus 3 squared. And instead of 3 times x, it's 3 times x plus 3, and then minus 5. As it says in the table, go with that table. Replace all the x's with x plus 3. Cool. We'd love for you to pause the video for a moment, see if you can do this one. I will ask you to remove parentheses and stuff like that. Sorry about that. Again, not very nice. But you should be able to kind of pull this off. Don't forget, square first, FOIL this out, then multiply it by 2 and go from there. I'll do it in a couple steps. If you have done it already, great. If not, no big deal. But I'll do it in a couple steps. So if I FOIL x plus 3 squared out, you end up getting that. So got that. Now I'll really remove all the parentheses. So I'm getting a 2x squared. I'm getting a 12x and an 18, a 3x and a 9, and then a minus 5. And so when all is said and done here, let's count them all up. I have a 2x squared. How about a 15x? And I'm seeing a 22 when all's said and done. 18 and 9, and then take away the 5. Again, if you're unsure, if you're like, wait a minute, that doesn't look right to me, well, let's check it out. No reason not to. So I'm going to go ahead one more time here. If you're still working on it, that's fine. I can be rather quick with our check. So I have that, and that, and that. And what did I say there? 2x squared plus 15x. Add that 22. Did it move to the right 3? I'm sorry, to the left 3? Yes, and it certainly did. There you go. Here's the original, and there's the new one. Transformation of the parent function. Okay, we're going a little overboard on this one, but do want to wrap up this notes worksheet on a positive note here. So let's do the last 2 examples. Stay with me if you can. So examples 2 and 3 now go into the graphical piece. So let's just start by looking at a point. So I have one original point on the graph of the parent function. So it says that negative 2, 6 be a point on the function y equals f of x, basically our parent function. Determine the corresponding point based on the transformation. Well, here's what I would ask you to do. Let's get just a coordinate plane off to the side here. And I'm going to graph this. I don't do this all that often, but let's graph that point. And let's just see. So negative 2, comma 6. And I'm going to just try to make it as large as possible there. There it is. Now what I want to know is what is the ordered pair based on each transformation? Where's the corresponding point? Where does this point go? So the first order of business is for you to get comfortable with notation. And I guess I would ask you this. If you can look at this and tell me which of the 6 transformations it is, then this becomes a piece of cake. So take a look at it, stare at it, think about input versus output, that narrows it down, and think about shift versus reflection and stuff like that. Well, I would say this is a vertical shift, and it looks like it's down. So basically, that notation is telling me to take all of the points on the original function and move them down 5. So think about this. Here's my original point. You can do this nicely here. Take that original point, everybody, and move it exactly the way it says. Move it down 5. 1, 2, 3, 4, 5. There's the new point. Can I figure out the ordered pair right there? Yeah, of course. Instead of negative 2, comma 6, it looks like it's negative 2, comma 1. Now a couple things to keep in mind here. Anything that's vertical, which coordinate is it going to affect, x or y? Well, of course, the y. Vertical affects the y. And you see, in this case, all I had to do was take 6 minus 5, and I get my new y value. Negative 2 stays the same. So it's that whole input versus output, x versus y. Okay, good. Let's see. Which of the transformations is this? Well, definitely, first of all, it looks like an input change, doesn't it? And it's one of the reflections. I see it as a y-axis reflection. So a couple ways to go about this. You can think of the table there, of course. Which coordinate changes when I reflect it over the y-axis? Well, of course, because it's an input change, it's the x that's going to change. And we already summarized this on the front side, but if I just reflect this over the y-axis, it looks like it just moves over here. There it goes, quick reflection, and I'm at that piece right there. And so that would be 2, comma 6. And if you notice what it says on the table on the front side, it just says all of the x's change to their opposite, and that's what happens here. Instead of -2, it's +2. Cool. Letter C. Which of the 6 transformations is this? Well, I'm hoping you would agree it's a horizontal shift. Left or right? To the right. So in this case, it's going right 7 units. And again, think about that piece. If it's going to the right 7 units, 1, 2, 3, 4, 5, 6, 7, looks like it's out here. And I'm getting, if I move it to the right 7, so it was at -2, if I go right 7, it goes all the way to +5. And so it's 5, 6. There you go. Nice. Again, horizontal, input, X is changing. The Y stays the same. All right, last 2 here, guys, and then we'll get to example 3. Which one do you have in this case? -f of X. I'm hoping that you really know that table pretty well at this point, but that seems to be one of the reflections. It's the X-axis reflection. So we're going to take this point and very simply just reflect it over the X-axis. When I reflect it over that X-axis, it is definitely moving vertically. So it's the Y value that's changing. Again, we said it before, it's an output. And it looks like instead of -2, 6, it's down here at -2, -6. I'll just go ahead and do that like I've been doing. So -2 and -6. Awesome. One more, just for good measure. See it, guys. See the notation. Let it all sort of speak to you pretty well here. Which way is this going? I'm seeing it as a horizontal shift. Left. Again, it just kind of jumps off the board at me. As soon as I see this notation, it's an input, it's horizontal, plus moves it to the left. Absolutely great. And so as a result, let's just move that point 1 to the left, and it goes right there. And so as a result, I've got -3 and 6. Notice the X changed, the Y did not. And we'll kind of talk about sort of in a little more detail, hopefully on the next notes worksheet, Y plus moves it to the left. And it's all based just really on how functions work. All right, good. We're ready for one more. A little longer on this lesson, my apologies on that, but really just developing everything conceptually today. So example 3, use the graph. So now instead of just a single point, what do you say we look at just the graph of a function, just something pretty generic in nature there. And could you draw the graph of the transformation? All right. Again, see the notation, everybody. So create your new function by taking the old function and adding 2. What is the graphical consequence of doing that? I'm hoping you would agree that this is a vertical shift, moving up. So all you have to do is take the infinite number of points on the graph of this function right here and move them up too. And that's it. I'm going to go ahead and do that. I've got to track a few of these points before. I'm going to try to work to some degree left to right. So 1, 2, 3, 4. So kind of move this point up to, this point up to, this point up to. And let's see if we can draw it. So let me see if I can pull that off, and you guys do the same. So it was down here, down at this piece. Move it up to, and it's right there. Let's get a couple others. So this point, I'm going to move up to. That would move here. Just trying to catch some of the key points. This point at the origin now goes up to. So something like that. This point up to. Okay, almost there. And then this one out here, move that up to. Again, an infinite number of points, but I think we can kind of work this out. Should do that, and then that, and then that. Good. Transformation based on the description. And last one, letter B. Which reflection is this, guys? Have it be automatic at this stage. Is it an X-axis reflection or a Y-axis reflection? And I'm seeing this as a Y-axis reflection. It is a horizontal change, And so it's going to reflect over here, over that y-axis. So let's take all of these points and just reflect. So these points move over here, these points move over here, and we've got it. So instead of -4, -2, it moves all the way out here. I see that going here. Instead of this point right here, this is going to move over. It's going to reflect over that y-axis to, I'm seeing it about right there. The origin, obviously, stays exactly as is. This point reflects over the y-axis, and this point reflects over the y-axis. And we have our winner. There you go. Okay, wow, we developed a lot here today. Let me just write this piece in, that this was a y-axis reflection, and that should round it out. My apologies that it was a little longer this time around here, but I think we set up some good math. There's really some good stuff with this. So try some things out there, know the table. And please, if something's not clicking, ask. I can definitely help sort of clarify anything. Well, thank you very much for listening, of course, as always.